How does PCA use SVD for dimensionality reduction? Imagine trying to find the most important features in a huge pile of data. That's what principal component analysis does, and it uses a clever mathematical trick called singular value decomposition to do it. Let's start with a big table of data where each row is a feature and each column is a sample. First, PCA makes sure the data is centered by subtracting the mean of each feature. This step is important because it aligns the data around zero, making the analysis more accurate. Next, PCA applies singular value decomposition to this centered data. Think of SVD as breaking down the data matrix into three smaller matrices called U, S, and V transpose. The matrix U contains the directions that are orthogonal or at right angles to each other in the feature space. The matrix V transpose holds the directions for the samples, also orthogonal. The matrix S is diagonal, with numbers called singular values that tell us how much variance each direction captures. These singular values are related to the eigenvalues of the covariance matrix of the data. The bigger the singular value, the more important that direction is for explaining the data's variance. The columns of U are called principal directions or principal components because they point out the main ways the data varies. To reduce the dimensions, PCA picks the top few singular values and their corresponding vectors. For example, if you choose the top three, you keep the three most important directions. This gives you a new, smaller set of features that still hold most of the information from the original data. When you project your data onto these new directions, you get a simplified version of the original data. This makes it easier to visualize, analyze, and use in machine learning tasks like clustering or classification. In the world of artificial intelligence, especially with large datasets like images or text, PCA helps to compress data and speed up calculations. It's like squeezing a big, complex picture into a smaller, clearer one without losing the main story. But it's important to be careful. Reducing dimensions can sometimes hide important details, especially if those details are subtle or relate to minority groups. So, applying PCA thoughtfully ensures you keep the right balance between simplicity and accuracy. In summary, PCA uses singular value decomposition to find the main directions in your data. It then keeps only the most important ones, reducing the number of features while still capturing the essence of the original data. This process makes complex data easier to work with and is a key tool in many machine learning projects.